This is a catch can test to measure irrigation uniformity and irrigation rate. I am Dr. Phil Busey at Miami-Dade College, Kendall Campus Landscape Technology Nursery. Let us begin, and I will refresh you with the details. To begin, I will turn on the irrigation zone. I will check the time, which is 1:55 p.m. and I will check the pressure, which is 30 pounds per square inch. This irrigation zone consists of 10 spray heads. There are 2 full circle 360-degree nozzle equipped heads in the middle, and the 8 perimeter heads each has a nozzle which is a half circle 180-degree perimeter. An irrigation zone like this that is properly designed should match the table requirements in the manufacturer's guidelines, and it does. The pressure is 30 pounds per square inch, and the spacing of the sprinkler heads is 15 feet, and they are on a triangular grid. What we are doing here is 2 things. One is we are measuring irrigation uniformity, and the other is measuring irrigation rate. Irrigation uniformity is based upon the variability in water catchment in at least 25 or more cups such as this. And the irrigation rate is determined by dividing that information by the run time, which we're recording. A properly designed sprinkler system, according to the table requirements in the irrigation manufacturer's specifications, is going to provide considerable overlap. Typically we say head-to-head coverage, but what this means is that within each of the bounded 10 triangular areas in this irrigation zone, water is being received by every spot from at least 3 different sprinkler heads. A sprinkler head tends to distribute water heavily near the center and more thinly near the outer reaches. But because it's overlapped with adjacent sprinkler heads, there's a stacking of those thin distributions of water among the different sprinkler heads, and so there's more of a level distribution overall. The actual layout of this particular set of catchment cups in this catch can test is a rectilinear grid, which is easy for record keeping, but I have randomly offset the distances of the catchment cups in different directions so that I can more evenly represent the entire area. Irrigation uniformity is very important because it's connected with efficiency. A very high 100% efficient irrigation system, which would have 100% irrigation uniformity, is not going to have any areas that are over-irrigated or under-irrigated. That's why it's so much more efficient. Now, you can't necessarily take irrigation uniformity and apply it directly to efficiency. When one goes up, the other goes up, but not exactly on a numerical basis. The reason that irrigation rate is important is that once we know the irrigation rate of an irrigation system, we can accurately schedule the irrigation run times for each zone to provide just enough water to wet the root zone of the plants. Not any more, not any less. And that's another way of improving the irrigation efficiency in addition to having a more uniform irrigation system. Now we'll run this for a number of minutes, turn it off, measure the water in the cups, and I'm going to use volume because unlike the parallel sidewall cans that would once be used, these cups have an angled sidewall. But we could just as accurately measure volume anyway and divide that by the catchment area. The cups have a diameter of 9.5 centimeters around the top of the cup. That diameter is divided by 2 to find the radius. The radius is squared and multiplied by pi, which is 3.14. That would be how we find the area of the top of the cup, and we divide the volume captured by the area of the cup to find the depth. And then we can divide that again by minutes, runtime, multiply by 60. If we want to have inches per hour, any other unit of measurement can be converted to very easily. So let's go ahead and let this run for 15 minutes, and I'll be back to turn off the irrigation zone and measure the catchment in each cup. Thank you. Okay, it's been 15 minutes, and I am now going to measure the catchment in the cup. I might at this point mention that each cup has a little stone inside. That's how, for the most part, I keep these from getting blown over. And I do want to make sure that both the cup is level to more accurately represent the irrigation rate, and that my measuring instrument, in this case I'll start with the beaker, is held level as well to give accurate measurements. And I'll record my values in a rectilinear arrangement the way these are laid out. So the first cup has 65 milliliters, which I will record here. And this is the last cup. The catchment is 51. Okay, so these are the values for 32 catchment cups. Fortunately, none of them got stepped on, none of them got blown over by the wind, and we have a somewhat rough listing of the milliliters per cup. I'm going to write the diameter, which is 9.5 centimeters, the date, which is the 15th of January 2017, and the pressure is 30 pounds per square inch, 15-foot spacing, and most of the other details will be documented subsequently. Now that we have our catch can data representing the milliliters per cup, let's have fun with the numbers. Let's put them to work. Remember, the pressure was 30 pounds per square inch, cup diameter was 9.5 centimeters, cup area, according to pi r squared, was 70.88 square centimeters, and irrigation runtime was 15 minutes. The average of the cups, of which there are 32, is 59.16 milliliters, which is the same as 59.16 cubic centimeters. From this, we calculate the precipitation rate. Precipitation rate, or irrigation rate, is the volume, 59.16 cubic centimeters, divided by the catchment area, 70.88 square centimeters per cup, divided by the run time of 15 minutes, and multiplied by a conversion, which is 60 minutes per hour. By canceling the units and multiplying and dividing these numbers, we get 3.34 centimeters per hour irrigation rate, which, when we divide that by the conversion of 2.54 centimeters per inch, we get 1.31 inches per hour. Compared with the manufacturer's value, which is a book value of 1.83 inches per hour for these particular spray heads at 30 pounds per square inch pressure and a 15-foot spacing on a triangular layout. Our observed 1.31 inches per hour was only 72% of the expected. How do we explain this deficiency? One evidence for the possible reason for the deficiency in irrigation rate is the very low values on the south side of this irrigation catchment layout. If you look on the left, there are low values such as 17, 20, 21, 29, and 39, which are all within the lowest quarter. This was a wind-affected area, as you can see by the movement on the ground of shadows of palm fronds. It could be that because we had half-circle heads around the perimeter of this very small irrigation zone, and there was moderate breeze on the day the test was done, that this may have been a wind effect. We'll get into that in a minute. To find the actual distribution uniformity, we go back to the catch average of 59.16 milliliters per cup. We look at the lowest 25% of the catchment cups. So since there are 32 cups, we look at the lowest 8 of these values. And you can see some of the really low values. We'll go pick those out, highlight them in red, and take an average of those 8 values. And the lowest quarter are 32.5 milliliters on average. Divide the lowest quarter by the overall average to get distribution uniformity, which is 54.9%, which is poor. But let's think again about the southern end there, where I say there was probably a wind effect. And just for curiosity, let's ignore those values. And there we have 24 cup catchments with a reassignment of some of the lowest 25% of the values. The new catch average, ignoring the wind-affected heads on the south, shows that the distribution uniformity was good elsewhere. The catch average was 66.25 milliliters, which was increased by dropping the low values on the south. The lowest quarter was much increased. Those 6 cups averaged 50.17 milliliters, and the distribution uniformity has risen to 74.7%, which is good. This is a kind of problem that we often do run into, but this is why we do a distribution uniformity test, to see where we might have a problem and how big it is. In addition, it makes the rate look better. Now the irrigation rate is 1.47 inches per hour, and compared with the book value of 1.83 inches per hour, we observed 80% of the expected precipitation. This is a small irrigation zone, obviously greatly affected by wind. And anyway, this is how we find precipitation rate, and we also find irrigation uniformity and can solve problems to have a more efficient irrigation system. Thank you for listening.